Good morning. Welcome to Krishna's classroom. Now we continue with our discussion on Lebesgue integration. Recall, we started off by looking at Riemann integration, trying to find out the what you call inadequacies of that and the reasons why we should essentially think about a process of integration fresh, but we could do it from there and related to that, and we have successfully gone through the process of developing the Lebesgue integration theory, which is essentially a generalization of the Riemann integral, or at least that is what we wanted it to be. Okay, so we have to finally check that we are on the right track. Okay, so we want to look at the Riemann and Lebesgue integrability together. Okay, so in this context, now if you look at the Riemann integrability, then we found that we had two types of integrals related to it. One is the so-called upper integral and the lower integral. Now, the technique was essentially to define integral of what are called step functions and then approximate the given function from above and from below by step functions. And then we introduced what are called or what is called the upper and lower integrals, and then we said that the function is Riemann integrable if this upper integral and the lower integral coincide. Otherwise, it is not Riemann. Now, if you carefully examine the track of Lebesgue integration, then you see that we have more or less followed the same track. But now we improved the scope of subdivision of the set. That is the domain of the function. Okay, and we introduced or extended the concept of length to a larger class of subsets of the domain, and we identified what are the so-called measurable sets, and then at that stage we identified that if you are working on intervals, then the Lebesgue measure is essentially the length of the interval. So once again, we have approximated the function from above and from below, if possible. I mean, sometimes it is not possible to approximate it from below. From above, if we are looking at only non-negative unbounded functions, then it is not possible to approximate from above, but from below you can approximate it through what are called simple functions. Okay, so the role of step functions is now here taken by a wider class of functions named simple functions, which is more or less of the same type, and every step function that appears in the context of Riemann integral is a simple function. But the class of what are called simple functions is much wider than that. Therefore, you get a much better reach. And again, a sort of approximation using simple functions is worked out exactly like we proceeded in the case of Riemann integral. And then we asked whether the limit exists or not. This kind of questions were asked. So, at each stage, that is at the construction of the measure and so on, we have checked that we are closely following the path we had worked out in the case of Riemann integral. Lengths were generalized to what are called measures, and you had measurable sets, so the intervals were replaced by what are called measurable sets, and so on. So it's the same sort of but same sort of work that we have done, but you know that we now have a much sharper reach to a wider class of functions, mainly because we are trying to approximate the function by using this broader class of functions. That's what. Okay. And now it is time to once again go for the characterization of Riemann and Lebesgue integrability. So that is the objective of this talk. So first we start with a theorem which enables us to look at this problem. But before that we prove a lemma. So I think I'll do this because we had used 5 earlier. Let and psi n be measurable functions, be sequences of functions such that phi n is increasing and psi n is decreasing. So what we have is we have two sequences, one phi n and the other one psi n. Phi n is an increasing sequence, they are all measurable functions, and psi n is a decreasing sequence. On a measurable set, let f be a function defined on E such that that means for each n phi n is a lower bound for f and psi n is an upper bound for f. So f is essentially squeezed between the measurable functions phi n and psi n. Okay. If limit n tending to infinity integral over E equal to 0, then the sequence yn converges to F pointwise almost everywhere, and psi n also converges to F pointwise almost everywhere on E F is integrable on E F is integrable on E and limit n tending to infinity integral equal to and in short, any function that is squeezed between phi n and psi n on E where phi n and psi n satisfies this requirement. This is the crucial condition. There are two things, phi n and F is squeezed between these two, and this is 0. Then we have phi n converging to F pointwise from below and psi n converging to F from above pointwise almost everywhere, and the corresponding integrals. You see, integral F is equal to limit n tending to infinity integral phi n. It is also equal to limit n tending to infinity integral over E psi n. Now this is the result. So every F that is squeezed between phi n and psi n would satisfy this. I just give a schematic diagram. It is not the proper diagram. Just using an interval here, but it's not interval. It is just what you are saying is E is a measurable set. So you have, this is phi n, and you have psi n is rather psi n, and then you have an F that is squeezed between 0. Okay, and you have the property that this particular area, is goes to 0. That's what I said, that both phi n and psi n, the f is squeezed between them. And if this is so, okay, then what you can infer is that such an f is a measurable function, and phi n point-wise almost everywhere converges to f, psi n almost everywhere point-wise converges to f, and this integral of f can be computed either using phi n or by using psi n. That's the result that you have. Okay, let us prove this result. So you take a x belonging to, so we will define phi star of a new function equal to limit n tending to infinity this could be even infinite, because I am not assuming that these are bounded functions, and so also you define psi star Now, the first thing that you observe is that phi star and psi star are well defined, and we have assumed that phi star is monotonically increasing, phi n is monotonically increasing, since phi n is monotonically increasing and is monotonically decreasing, measurable and they are extended real value, that means they take values in R star. R star is R union plus infinity and minus infinity. Both phi star x and exist as extended real value, So the crucial supporting conditions are phi n is monotonically increasing, psi n is monotonically decreasing, and they are extended real valued. Therefore, you get phi star and psi star as extended real valued functions. Okay, so that is well defined. Further, we also have the following. See that phi star is less than or equal to psi star. Okay. Now, both phi star and psi star are measurable functions because they are the pointwise limit of measurable functions. What is the reason? Since they are the pointwise respective. Okay. So, what more we have? We have phi n is less than or equal to phi star, and that is less than or equal to f, and that is less than or equal to psi star, that is less than or equal to psi. Now we make use of this condition that we have in the theorem. Okay. By monotonicity, and the linearity of the integral, you see, psi n minus phi n is integrable. Psi star minus phi star is also integrable. So what you have is this: 0 less than or equal to integral over E phi n. And this is true for every. Therefore, zero less than or equal to integral over E psi star minus phi star, which is less than or equal to limit n tending to infinity of integral over E psi n minus phi n, which is equal to 0. What does it mean? It means that limit phi n is equal to limit psi n, and you see that f is squeezed between. Therefore, you have is non-negative and measurable. and non-negative, measurable, and equal to 0. We have everywhere. Further, we have phi star is less than or equal to f, less than or equal to 6, which implies converges to f, and almost everywhere pointers. So that implies f is measured. Therefore, one can talk about the integral of, okay. Further, it's a simple observation. 0 less than or equal to f minus phi 1. Minus phi 1 is non-negative. And this is less than or equal to, because psi 1 stays above f. Therefore, this is psi 1 minus phi 1 on E. Now, psi 1 and phi 1 are integrable. Over E. We have f is integrable over. That is because you see that this is less than or equal to integral over f minus phi 1. See, this is squeezed between these two. Okay, this is integrable, therefore, and phi 1 is integrable, therefore, f is integrable. So, we infer this from the integral comparison test. So this is the crucial conclusion that we make, and therefore you have 0 less than or equal to psi n minus phi n is less than or equal to less than or equal to integral over E which is equal to integral over E which is less than or equal to integral over E phi n. And this, of course, as n tends to, this is true for every n. Therefore, this goes to 0. Therefore, you have no further. This is also true. Therefore, what you have, see, this goes to 0. This goes to 0. Therefore, what you have? You have limit n tending to infinity integral over E f, and also equal to limit n tending to infinity that means you can approximate in this case both from above and from below using sequence of functions, or if you have such sequence of functions, then you see that the limiting function is essentially squeezed between these phi n's and psi n's, and it is integrable, and the integral can be obtained either by approximating from below by the integrals of phi n, or approximating from above by the integrals of psi n. Now, this is what we prove. Okay, this is a useful lemma which we are going to use. Now we link the integrability and the measurability. Okay, at least for a class of functions. because eventually our objective is to consider what are called Riemann integral functions and work on them. So we are eventually interested on functions defined on finite measure, because it is going to be on intervals, bounded intervals, and then bounded functions. Therefore, we are going to talk about what are called bounded measurable functions defined on sets of finite measure. Okay, so let us move the theorem. I'm following the same numbering as you have in what is called the book by Royden. Okay. Let F be a bounded function on a set of so we are assuming that E is of finite measure, E is measurable and is of finite measure, and F is a bounded function defined on a set of finite measure. Then F is Lebesgue integrable if and only if F is measurable. So that is the conclusion. F is Lebesgue integrable if and only if F is measurable. This is the conclusion. Okay, we prove this result. Now, I think before that, I'll make a remark. Suppose F is not a measurable function. Take a bounded, non-measurable function. This is quite easy to produce an example, because we are now told that if E is a measurable set of finite measure, then there exists a subset A of E such that A is not measurable. So, I'll just make a remark. It's not integrable. So for that, take note that measurable and of finite measure, there exists a subset A of which is non-measurable. then the characteristic function of A restricted to E is non-measurable. But bounded. Because it takes the value 1 or 0. Okay. It is non-measurable. And what about the integral of and chi A is not integral. So let us prove this result. So what it says is that, what this example shows is that there exist functions which are bounded but not necessarily measurable, and therefore not integral. Okay. So let us prove this result. We call that shown earlier. That a bounded measurable function on E, which is measurable, measure of E, finite, is integrable. That is, what we have proved is this, that is measurability. Integrable. For the particular class of functions we are considering, that means they are bounded measurable functions on a set of finite. Okay. So now what remains to be shown is the converse. So let us claim that is the converse, that integrability implies measurable. This is what we want to do. Remember, E is a measurable set with finite measure, and we are assuming f is an integrable function on E. Okay. Suppose integrable. Then what we have is there exists sequences, simple functions phi n and psi n, for which such that because you can write psi n minus phi n as psi n minus f plus f minus phi n. Okay, and integral phi n goes to integral f, integral psi n goes to integral f, therefore this is true. Okay, now that is the way in which you prove it, as you can put here. Now integral of this is equal to integral of this plus integral of this by the what you call linearity, and then as n tends to infinity, this goes to this integral goes to 0, this integral goes to 0, therefore this goes to 0. So since the maximum and minimum of a pair of simple functions are again simple, we can repeatedly apply this, okay, and take the maximum and minimum or a finite set of simple functions which is also simple, okay. And replacing and psi n by maximum of over phi I and minimum of one less than or equal to I in psi I. So we replace this by the set of functions. So replace, of course, phi 1 you retain as it is, and then phi 2 you replace by the maximum of phi 1 and phi 2. Phi 3 you replace by the maximum of phi 1, phi 2, phi 3, and so on. So you get another sequence. Okay, they are again measurable functions. And but what is the gain that you have? You get a monotone sequence of measurable functions. Okay, so the new set that you obtain is a monotone set of measurable functions. Okay, so we may suppose psi n monotone increasing and decreasing respectively. Okay, so you can essentially approximate f from below by monotonically increasing measurable functions and f by monotonically decreasing simple functions from above. These approximations are possible. And you see that both, these functions, they are simple functions. These are simple functions. Therefore, we can, without loss of generality, we can assume this. Now, apply the preceding lemma. That is lemma 6. We have phi n f pointwise on E and that implies because all these phi n's are measurable functions. Okay? Simple functions are measurable functions. F is measurable because it's a limit of pointwise limit of a sequence of measurable functions. Further, so we can directly apply the lemma 6. We have limit n tending to infinity of integral over E this is equal to integral over E, that is f is measurable. Sorry, that is This is so we were trying to prove what we were trying to prove that a measure of the integrability implies measurability. So that we have proved the previous step itself. So this is just the observation. Okay. So thank you very much. I think let me stop here. Okay. We'll continue with it in our next lecture and explore this problem of connecting Riemann integral and the Lebesgue integral in the context of integral.